When you operate with convolution layers in your deep neural network, have you ever asked yourself, how is it possible that you can use these layers and it is independent if you at first feed the image to all of the layers and then shift it a little bit, or if you take the image, shift it a little bit and then feed it to all of these layers, that there is a translation equivariance in those convolution layers. We didn't program it. So where the hell does it come from? And this symmetry, in our case a translation symmetry, is preserved by each layer, so making it possible to exploit it not just in the first layer, but also in the higher layers of the network. So the main question is now, why are symmetries in neural network layers preserved? Amazing. To answer this, we have to look at the mathematical definition of a group. A group consists of a set of elements G. We have defined an operation, either an addition or a multiplication. The group is closed under this operation. The group has an inverse element. The group has an identity element. And there is the rule of associativity within the group. This is the definition of abstract algebra. What is a group? Now, if we're going to use this definition, we will see that the definition of a group is the simplest definition possible that will let you solve a basic equation, a mathematical equation. And if you say, how is this possible? Let's have a look here. We have an equation x plus 3 equals 5. And here are listed all the steps that you need to solve this equation. And each step is defined in the property of a group. Now, are multiples of 7 under the operation addition a group? Yes. Are odd integers under the operation addition? No, they are not a group. And the integers under the operation multiplication are also not a group. So you can test out, if you look at a particular set of elements, if they form a group or not. Now there's Lagrange theorem, and that is a very powerful theorem, because you want to have a group, you want to know the inner working of this group, you want to know the subgroups. And Lagrange theorem tells us if a group H is a subgroup of a finite group G, then the order of H divides the order of G. The group homomorphism, you will encounter this a lot. A group homomorphism is a function between two groups that identifies structural similarities between them. This is really important for you to know if two groups are structurally similar or not. And of course, there's mathematical definition. Let's say we have two groups, a group G with an operation and a group H with a different operation. Now, F is an homomorphism from G to H if F of x times G, and notice here the operator is a function of G, equals f of x times f of y. Notice here the operator is from the group H. If this is what you can confirm for your set of elements, then you have a group homomorphism, a function between two groups that identifies structural similarities between them. Another example you see here, you have the real numbers under the operation addition with the identity and the positive real numbers under multiplication. And you can show that this is a group homomorphism, F from G to H. Another wording you might encounter is the kernel of a homomorphism. Now, it maps to the identity in H, and a kernel definition is given here, but let me summarize it in some words. A homomorphism sends identities to identities and inverse to inverse. But there are multiple elements in G which all map to the identity in H. Those elements we call the kernel of F. The kernel is a property of the homomorphism. Let me show you another beautiful definition. Vector spaces are commutative groups under the operation addition. So we have commutative groups under addition that define vector spaces. Here you have the classical definition of a vector space. You have a field of scalars, and V is the vector, and then you have the distributive properties, the associative properties. You have the scaling by one element. And if you look at this, you understand that this is a commutative group under the operation addition. And now finally we are able to answer our question we had at the beginning of this video. The important properties of a convolution, such as the equivariance, arises primarily from the underlying group structure. And this is a deep insight into the configuration and the mathematical power of a group structure that we apply in neural networks. Convolution operators or operations used in convolutional neural networks are equivariant to translation, and please notice here translation, but not to other transformation such as rotation. So you have to watch out for the specific symmetry given your group.